say a few comments about homework 2, which is due at midnight. So this is just a completely general statement, but it may help you a little bit with homework 2, question 2. So just recall that in Bayes' law, we are typically comparing different model states, right, in terms of their posterior probabilities. So it's based on the observed evidence, does that favor a higher posterior probability for this model candidate versus that model candidate? And to turn that into sort of the precise mathematical language, we would have some model variable, which here I've called gamma, and it would have different possible model states, right? So in homework 2, question 2, we talked about these model states in terms of a match model and a mismatch model. And these are two competing possibilities for what could really be emitting our observed data, right? In other words, it might really be the case that the two samples are from the same person, or it might not be the case that they're from the same person. And so we're trying to measure the evidence for those two possible hidden states, right? So the language that we were using in that question was alternative models, match versus mismatch, which you could basically view as different possible states of our model variable. Okay, so typically in Bayesian inference, we would be calculating a posterior probability for a particular value of gamma, our model variable. For example, gamma equals match, given the observations. And in this particular case, there was an additional parameter that you were basically told to treat as kind of fixed, namely the population allele frequency f for the marker. So one thing that is very common to do in statistical inference is when we're explicitly comparing just two alternative states, really all we have to do is talk about their so-called odds ratio. And instead of using a posterior probability for gamma given XSF, we might have the posterior odds ratio of, in the numerator, probability that gamma equals match given XSF, divided by, in the denominator, probability that gamma equals mismatch given XSF. Okay? And of course, by Bayes' law, both of those posterior probabilities, in Bayes' law, they have the same denominator, right? In other words, the summation over all possible model states gamma. So those denominators just cancel, and this odds ratio just turns into the numerator divided by the numerator for our two different models. In other words, the likelihood of the observations given the model times the prior probability for the model for match versus mismatch. Okay? So one further simplification that you will frequently see in, for example, research papers or in actual statistical computation code is if we're assuming that the priors are equal for our models. In other words, we're not even taking the priors into account. We just basically treat that factor as canceling, vanishing from this odds ratio. And now what we're talking about is effectively, if we were to make that assumption, then our posterior odds ratio would just be equal to our likelihood odds ratio. In other words, just the ratio of the two likelihoods of the observations given match versus mismatch. So what you see in homework 2, question 2, was basically a simplification of kind of this form where we start to talk about just this likelihood odds ratio. Question?
If they don't say anything, are we allowed to assume that the two models are equally similar?
That the priors are equal? So this question didn't even ask you to compute posterior probabilities, period. It just said calculate this likelihood odds ratio, right? So, when you take a look at this form, you can see that basically the signal favoring match versus mismatch can come from basically two places, right? Either it can come from the prior or it can come from the likelihood, right? So when we talk about this piece, we're basically saying, what is the evidence telling us? What is the observable evidence telling us, as opposed to what is just coming from what we assumed for our prior, right? So that's one way of thinking about it. In general, in real life, we probably shouldn't assume equal priors silently. In other words, if that's what we're assuming, we should say that very explicitly. And this is very commonly done, and it's called an uninformative prior. In other words, that basically we're treating the prior probabilities of different possible model states as uninformative, equally probable. That's a common assumption. If you make that assumption, you should make it very explicit, stating this is what we're assuming. In many real-world situations, that might not be an appropriate assumption, right? There might be data telling you, no, they're not equally probable. Other questions? Okay. So